Rockets!
How do they work?
Let's take a closer look at that rocket. A rocket is a vehicle that uses reaction mass, such as rocket fuel, to propel itself. This rocket isn't going anywhere, but it's demonstrating the engine nicely. The engine fires mass backwards, resulting in force forwards. As rockets need to fire mass backwards, they have to carry much of this mass as fuel. Chemical propellants, like normal rocket fuel, tend to run out quickly because engines need to eject a large amount of mass very quickly. Fins near the back of the vessel keep it pointing forward, even during extreme aerodynamic stress. Getting into space takes a lot of velocity. And because this requires heavy fuel that runs out quickly, staging is the only option. Let's see an example mission. This rocket is headed to orbit. In order to get into space and stay there, the vehicle needs to build enough speed to orbit. This also requires you to escape the atmosphere's drag and is done first in a launch by flying straight up. You may have noticed that this rocket has some very large fins on it. This is because the upper stage already has fins on it and will flip the entire vehicle around if the center of lift is not balanced behind the center of mass. Here we begin the gravity turn. In order to orbit a planet, you don't simply fly upward, but sideways. Why? Because orbiting is when you have enough velocity to be in free fall, but constantly miss the planet below you. Now that it's out of most of the atmosphere, the next step is to build speed parallel to the ground. This is also where staging is important, as fuel in rockets are heavy and inefficient. Stacking them in staging allows much more acceleration than one stage. The upper stage separates from the booster and now has much more potential to accelerate with its assistance. This is a ballistic arc. Much like the path of a cannonball, at the current speed, the spaceship will fly up to a maximum height and then hit the ground. In order to not land prematurely, the upper stage will have to build up enough speed for a stable orbit. So the upper stage engines are fired and it continues in the acceleration. The increased velocity increases the trajectory until it misses the ground entirely. And it's in orbit. This is a very basic rocket, and you might wonder, why do you have to throw away half of the rocket on the way up?
To answer that, we need to understand some basic rocketry principles, starting with delta V. Delta V, mathematically, refers to change in velocity, and in practice can be thought of as potential acceleration. As rockets are self-contained and inefficient, it is possible and necessary to calculate how much they can accelerate. This rocket has 170 meters per second of delta V. That means that this vehicle will be able to accelerate to 170 meters per second if all of its fuel is used. This speed peaks at around 167 meters per second, as the calculations do not account for wheel drag and friction. Rockets in space work the same. The weight of the fuel, rocket, and efficiency of the engine are all calculated together to find the potential acceleration or delta velocity. Let's say you have a really cool car that you want to take all around the world. But you intend to do it without refueling once on your entire trip. That means all the fuel that you will need will have to be carried with you from the start. Carrying the extra fuel with you will mean a much heavier, less efficient, and bulky car. With all the extra weight and diminished efficiency, in order to go further, you will need to carry exponentially more fuel. As gas stations are not rare, this kind of vehicle would be ridiculous and inefficient. But in rockets, to get the delta V necessary to make it to space and to other planets, this kind of setup is the only option. So in practice, rockets are bulky, dangerous, expensive, and inefficient, and they're the only way to space we have. All of it hinges on the mathematical limitations of carrying your own weight and fuel, and having huge amounts of delta V needed to travel anywhere away from Earth.
Using the concept discussed so far, what does it take to get to the moon? The vehicle gets into orbit the same way as the rocket from earlier. Launch upward, then gravity turn. First booster stage separates. Ballistic trajectory grows as speed increases. The upper stage uses its fuel to accelerate further, nearing orbital velocity. It runs out of fuel and stage is dropped. The next engine ignites. The trajectory turns into an orbit. Now we need to get to the moon. To do that requires a transfer burn. That means accelerating the spacecraft, making its orbit eccentric enough to cross paths with the moon. As the spacecraft accelerates near the planet, the far side of the orbit extends further out. As the two objects orbit, they will intersect, and the spacecraft will fly by the moon. And projected flyby. Speeding things up again 4 times. From here, time is speeding up as the ship coasts its way to the moon. Now it's on a flyby trajectory of the moon, moving too fast to stay in orbit. So it accelerates backwards, having a reverse transfer effect. And a stable lunar orbit is achieved. Further deceleration brings the orbit into a ballistic trajectory, beginning the landing. Lander separates from the transfer stage and prepares to land. Without an atmosphere, parachutes won't do anything, so the only way to land is to slow all the way down. Mostly slowed down, the final step is to hover to the ground. Landing on a bit of an incline, causing for a bit of a rough landing.
Now to get home. To land on Earth again, we need to intercept it, much like we did from the Earth's orbit to the Moon. But this involves leaving the Moon and decelerating in our orbit to bring the far side of the Earth into the Earth's atmosphere. So accelerate this way relative to the Moon's orbit. Blasting off and accelerating opposite to the Moon's orbit. accelerate directly against the moon's velocity. This brings the lower end of the orbit as close as possible to Earth, leading directly into its atmosphere. As we enter the atmosphere, the only way to slow down this time is with air friction and parachutes. Right away, we begin to experience ram pressure heating. This isn't on fire. The atmosphere is being compressed against the craft so quickly that it heats up significantly. The only thing keeping the craft from burning up is the large heat shield at its base.